Hi, this is Dr. Roji. Welcome to a session on bipolar junction transistor. In this session, I'll explain the different types of BJT and how the BJT has grown up from the PN junction diode and the different characteristics of BJT. There are two types of BJT, the PNP and the NPN. As the name itself says, in the PNP transistor, conduction is mainly by holes. And in the NPN transistor, conduction is mainly by electrons. But the electrons mobility is much higher, almost 3 times that of the holes. So NPN is very popular, whereas PNP is not that much used. There are 3 terminals of the BJT, the emitter, base and the collector. The emitter is wide and it is heavily doped. As the name itself says, the emitter emits. What does it emit? It emits the carriers. The base is the thinnest of all and it is very lightly doped. The collector is wider than the emitter and the doping is lighter than that of the emitter but heavier than that of the base. The 3 configurations of the BGT are common emitter, common base and the common collector. The first configuration is the common emitter configuration. The input terminal is the base and the output terminal is the collector. What about E? E is a common terminal. So E is found in the input side as well as in the output side. The input voltage is thus measured between the base and the emitter, which is given as VBE. The output voltage is given as VCE, which is the voltage between the collector and the emitter. And the input current is the current which flows in the input terminal, which is IB. And the output current is the current which flows through the output terminal, which is IC. Right. The next configuration is the common collector configuration. As shown in the figure, the input terminal is base, output terminal is the emitter, and the collector is common to input and output. Input voltage is thus measured between input terminal and the common terminal, which is VBC. Output voltage is VEC. Input current is the current which flows towards the input terminal, which is IB, and the output current is IE. Same definitions which we had seen in the previous 2 slides holds good for this slide also. Yeah, we'll go to the next one, which is the characteristics of the BJT. First, we'll see the characteristics of the BJT in the common base configuration. Don't get confused as there are so many extra components. It is the common base. So as you can see, emitter is the input terminal, collector is the output terminal, base is common, and to the left hand side you see a power supply, which is the input power supply, and at the right hand side you see a power supply which is VCC, which is the output power supply. So this is the input characteristics of the BJT in the common base configuration. So input characteristics is drawn between input voltage and input current. As I had shown in the previous table, input voltage is VEB and the output input current is IB. Right, and this is measured by keeping VCB, which is the output voltage, as a constant. Have you seen this figure before? This figure resembles a forward characteristics of the PN junction diode. Am I right? Now, to this same figure, I'm going to make a change. I'm going to increase the VCB to 1 volt. When I increase the VCB to 1 volt, what will happen to the depletion region and the collector base? VCB is a reverse voltage. So the depletion width at the collector base junction will increase, which causes the effective base width to decrease. Since the effective base width decreases, the emitter current will increase. Why? It is because the recombination which takes place in the base has decreased. Right? Yeah. So as I had said, when VCB is increased to 1 volt, the curve shifts to the left. Now to the output characteristics of the common base configuration. Right, along the x-axis I have taken the output voltage, which is nothing but VCB. Along the y-axis I have taken the output current, which is nothing but IC, and the input current IE is kept as a constant. As you can see, there are three regions of operation: active region, saturation region, and cutoff. When the transistor is in the active region, the collector base junction is reverse biased and the emitter base junction is forward biased. So as you can see, in the active region, the current for a particular IE is almost constant. Even if you change your VCB, the current is not going to increase. It's because the collector base junction is reverse biased, right? You have observed the same thing in the case of the reverse biased diode. When the diode is reverse biased, even if you increase the supply voltage, the current doesn't increase. Okay, now I increase my input current from 0 to 1 milliamps. What is happening to the collector current? The collector current also increases. When I increase it to 2 milliamps, there is a corresponding increase in my collector current. So what can I say about the active region? In the active region, the collector current is independent of VCB. It depends only on the input current, right? Now come to the next one. In the saturation region, this is to the left of the y-axis. As you can see, there is a rapid increase in current. For a small change in VCB, the current IC increases rapidly. Why? It is because both the junctions are forward biased. Come to the cutoff, which is the hatched portion shown below 0 milliamps. The current is almost zero. It is again because both the junctions are reverse biased. Okay. And which is the preferred region of operation? Of course, the active region is the preferred region of operation. Why? When the biasing is in the active region, current increases. The output current increases only when my input current is increased. So IC increases when my IE is increased. So this is the preferred region of operation. And as I said, what does it resemble? Every curve resembles the reverse characteristics of the PN junction diode. Next, we'll see the characteristics of the BJT in the common emitter configuration. I hope you remember whatever we had seen about common emitter. Base is the input, collector is the output, right? And input characteristics of the BJT in common emitter. Input characteristics, as we all know, is drawn between input voltage and input current. For the common emitter, VBE is the input voltage and IB is the input current, right? As you can observe, IB is very small in the range of microamps due to the two reasons which we had seen in one of the previous slides. The base width is very narrow and the doping is also very less, right? So as we had seen in the previous configuration, this curve resembles the forward characteristics of the PN junction diode. So initially my VC is 0, I get this curve. Next I increase my VCE to another voltage, to a greater than 0 voltage. What happens here? The curve shifts to the right. We'll see what is the reason for this shift, right? So I'll take a constant VBE. I project a line upward. It hits the first one. VCE is equal to 0. I project it towards the y-axis and I find that IB is almost 200 microamps. I take the same point again. I project the point at which this line hits the VCE greater than 0 volts to the y-axis. This is 50. What do you observe? When the VCE increases, the base current decreases. Why does it happen? So this is the structure. Initially this structure is drawn for VCE is equal to 0. I'll draw the next structure for VCE greater than 0. The collector junction is reverse biased. the depletion width increases. When the depletion width increases, the effective base width will decrease, which causes my base current to decrease, right? And at the last, we'll see the output characteristics of the BJT in the common emitter configuration. It's the same as before. We have three regions of operation: active region, saturation region, cutoff region. And when you increase your VC very high, it enters the breakdown region. It goes to the breakdown region, right? One parameter which needs to be remembered here is the saturation resistance. Saturation resistance is the resistance which is taken in the saturation region. It is the ratio of delta VCE divided by delta IC. The next semiconductor device is the Jfet, the junction field effect transistor. There are two types of Jfet, the N-channel Jfet and the P-channel Jfet. We'll see the structure and the symbol of the N-channel Jfet. The N-channel Jfet has an N-type semiconductor bar, and on the top and the bottom of the N-channel bar we have doped with P-type impurities. This forms the gate, and one type of the N-type bar is the source, and the other end of the N-type semiconductor bar is my drain. This is the symbol of the N-channel Jfet. The gate has the arrow pointing inwards. This is to show that the gate is of P-type. And this is the P-channel Jfet. It's just the vice versa of the previous one. We have a P-type semiconductor bar, and on the top and the bottom we are doping with N-type impurities to form the gate, and the source and the drain are found on either side of the P-channel Jfet. And this is the symbol of the P-channel Jfet, with the gate having an arrow pointing outward. And this is the structure, this is the circuit which is used to do the characterization of Jfet. So as you can see from the circuit, there are two voltages, VGG and VDD. VGS is the voltage between the gate and the source, and VDS is the voltage between the drain and the source. IG is the input current, ID is the output current, and IS is the current through the common terminal, the source. We'll see the operation of the N-channel Jfet, and we'll start with the ohmic region. The ohmic region occurs when VGS is small and VDS is increased. So initially when VDS is increased, as you can see in the figure, electrons are moving from source to drain, right? So when electrons move from source to drain, there will be a movement of carriers from drain to source. Why is this so? Because we know that the movement of the electrons will be opposite to the movement direction of the current. So the current goes from source to drain. Sorry, the current goes from drain to source. So the drain is at a reverse bias potential, higher reverse bias than that of the source end. So whenever the reverse biasing is high, the width of the depletion region will be more. So the width of the depletion region, the drain end, will be greater than at the source end. So my depletion region will have this particular shape. Yeah. So the depletion region is wider at the drain end and it is narrower at the source end. We call it as a wedge shape. So I have shown one particular region, one particular curve of the characteristics. So as you can see here, as you can see, this is the ohmic region. So in the ohmic region, as you increase VDS, there is an increase in drain current. The same thing happens in the case of a resistor. So this mimics the operation of the resistor. So we call it as the ohmic region. And this whole process stops at the pinch off point. Yeah, as you can see, as the current increases, the depletion regions will move, and at one point they'll touch each other. That point is called a pinch off point, beyond which the current will be constant. Uniformly, and at one particular point they will completely touch each other. Complete depletion regions will touch each other. Yeah. So beyond this there will be no current. We call this as the cutoff region. Right? So this curve shows the complete characteristics of the N channel Jfet. We have seen about the we have seen about the saturation region, we have seen about the cutoff region, and in between we have the active region in which the current remains constant but it changes with an increase in the VGS. Right? So with this, we'll come to the end of this particular topic, where we see about the BJT and the Jfet, but it will not be complete if we do not see the difference between the both. Yeah. The bipolar device is a current control and the unipolar device is voltage control. That is the main difference. Yeah. The operation depends on the injection of minority carriers across a forward bias junction, whereas in the JFET, current operation mainly depends on the control of a junction depletion width. The next important difference is BJT is current control, whereas JFET is voltage control. Since in the BJT, the base current controls the output current, in JFET, the gate voltage controls the output current. In the BJT, the noise level is high because the current conduction is through the junctions. In JFET, the noise level is low since the current conduction is through the channel. BJT has a low impedance input impedance since the forward bias resistance is less, whereas JFET has a high input impedance because the gate is always reverse biased. In the case of BJT, gain is characterized by voltage gain. In the case of JFET, gain is characterized by transconductance. So with this, we come to the end of an interesting session where we saw about the semiconductor devices, BJT and the JFET. We'll meet again with yet another interesting session. Till then, bye.